Okay, so we were pretending that there was no interaction and looking at the main effect of drug. If we were to look at the main effect of biofeedback next, we would use the same means function and just give it a squiggly biofeedback, and we'd get the marginal means of biofeedback, which would just be present versus absent. Now it's averaged across all drug levels. And in fact, we don't need to do any more tests. There's no follow-up tests to do. The main effect of biofeedback is the only test that you can do because there's only two means. So if that's significant, that's the end of it. Getting the marginal means is useful because you can report them, but you don't need to actually do any more tests. The main effect of biofeedback is the test because there's only two means. Where are we? Yeah, so that was pretending, oh, I know what I wanted to say down here. A little by the way, when you have an F-test with 1 degree of freedom in the numerator, that means that you're just testing two means, as we are here, biofeedback present versus absent. And it just so happens mathematically that an F-test with 1 numerator and degree of freedom is equivalent to a t-test. I mean, it's the same math, actually, as a t-test. And in fact, F is equal to t squared. So an F-test, like here, with 1 numerator degree of freedom and 24 denominator degrees of freedom, as in here, which equals 22.15, which is this last value here. That's equivalent to a t-test with 24 degrees of freedom, and t would be the square root of that. T would be the square root of 22.5. If you literally took these data and ran it through a t-test, you would get a t value of 4.71. So they really are equivalent. That's a bit of ANOVA t-test training for you. Okay, let's go back to the actual data where there was a significant interaction effect. And let's follow it up with some simple main effects tests. So let's say we're going to do the simple main effect of drug within each level of biofeedback. So we'll test the effect of drug when biofeedback is absent, with just those blue data points. And then separately, we'll test the effect of the drug when biofeedback is present. So we can use our dplyr knowledge and filter our data and only include cases where biofeedback equal absent. Then we can run that through one-factor ANOVA. Blood pressure depends only on drug. And we can generate a summary of that ANOVA, and that's what we get. We get a test. It's only a one-way ANOVA now. Drug is the only factor, and it's a test of drug, and it's not significant. Yeah.
Can you say again the difference between simple main effect and just
a main effect? Yeah, so yes, so definitional. So a main effect is these two things. The main effect of biofeedback and the main effect of drug. The main effects are the things that are reported in the two-factor ANOVA before the interaction effect. So two-factor ANOVA has 3 tests, 3 omnibus tests. The main effect of factor A, that's A when you average across B. The main effect of factor B, that's factor B when you average across A. And the interaction effect A by B. So 3 omnibus tests, and 2 of them are main effects, and 1 is the interaction effect. The simple main effect is a follow-up test that you do when there is a significant interaction. When the omnibus interaction effect is significant. And that simple main effect is when you isolate one level of a factor and you test for the effect of the other factor within just that one level of the second factor. So testing for the effect of factor drug within this level of biofeedback absent, and then separately testing for the effect of drug within biofeedback present. So main effects are the things that are omnibus tests in the two-factor ANOVA, and simple main effects are tests that you do to follow up an interaction effect. Does that help?
Ish.
Ish.
So in the main effect, we're averaging across the other factor, and
That's right.
simple main effects, then we are
You're isolating.
as
That's
in, like,
right.
splitting the data set.
That's right, you're splitting it. Yeah, exactly. So in a main effect, you're averaging across levels of the other factor, or combining levels of the other factor, or ignoring levels of the other factor. In a simple main effect test, you're splitting off the data. You're isolating one of the levels of the factor and just testing the nodes. Okay.
So I understand that when there's an interaction, we want to look at the simple main effects because the regular main effects are not really interpretable
That's
given
right.
the interaction. But in your example, I thought we were doing an example where there was no interaction. We were pretending there was no interaction.
We're no longer pretending.
Oh, okay, I missed that.
Yeah, so, yeah. When we went from here to here, we're now no longer pretending. Sorry, I should have made that more clear. So now we're acknowledging, yes, there is a significant interaction effect, and now we're saying what to do. Okay, so we're going to test the simple main effect of the drug within each level of biofeedback. So we're going to isolate each level of biofeedback and test the effect of drug. So we filter the data to only include biofeedback absent. We run a single factor ANOVA on that, and here it is. So it tests the effect of drug in the subset of the data where biofeedback is absent. And what's the answer? P is greater than 0.05, so there's no effect of the drug when biofeedback is absent. So when we test just those three blue groups, they're not statistically reliably different. No effect of the drug when biofeedback is absent. So we stop. We don't do any pairwise tests because the simple main effects tests told us nothing to see here. So the second simple main effects test is now testing the effect of drug within the other level of biofeedback, where biofeedback is present. That's these three orange means. So we can filter the data and only include cases where biofeedback equal present. We can run that through a one-way ANOVA. And here's what we get. So here's an ANOVA that tests the effect of drug only within biofeedback present. And the answer is, it is significant. The p-value is less than 0.05. So there is an effect of the drug when biofeedback is present. What is the effect of the drug? We don't know yet. Now we have to do follow-up tests, pairwise tests, to find out what's different from what. So now we need to follow up that simple main effect with pairwise tests. We can do that with the pairs function and the EM means function, just like we saw before when we were looking at main effects. We can use the same kinds of functions. So again, we've filtered the data now, and we only include cases where biofeedback is present, the orange data. That was our ANOVA, that was our simple main effects test, and it was significant. So that means these three are not the same. But to find out what's different from what, we can now do EM means and feed it that ANOVA, the simple main effects ANOVA. And we get marginal means across levels of drug. I mean, we shouldn't call them marginal means probably because they're not averaging across biofeedback. They're isolated to just biofeedback present. We get the means of the three drug groups only for the orange data points. We can feed those EM means into the pairs function and tell it how to adjust for type 1 error, and we get the three pairwise tests of the drug within biofeedback present. And what we see is that when you compare drug absent with drug present, these two orange points, P is less than 0.05. So these are reliably different. Absent compared to high dose is also different. That's this orange one versus that orange one. But present versus high dose is not. this orange point versus that orange point, those are not different. Okay, so it seems a little complicated, but it's not actually that bad. When there's an interaction, don't look at the main effects. They don't make sense. You have to interpret that interaction and find out what is the nature of that interaction. So you can do simple main effects tests where you isolate each level of the second factor and do one-way ANOVAs on the first factor with each level of the second one. And this is the framework for how to do it. When that simple main effects ANOVA is significant, you can follow that up with pairwise tests to find out what's different from what. So, I mean, for sure, a two-factor ANOVA is more work in the end than a one-factor ANOVA. But the great power of the two-factor ANOVA is it allows you to detect these kinds of interactions. Right? If you were a drug company and you were testing this drug, and you recruited participants and they were sort of, 60% male and 40% female, because you were just randomly recruiting people from your company, it would be as if you're ignoring this I said male and female and then biofeedback present after. You would be ignoring that there are two categories here. And you would get some average of these. And maybe you would find the drug has some mediocre effect. Or maybe you would find that statistically it doesn't have an effect. And you would be missing out on the fact that, well, it does have an effect if you combine it with biofeedback, and it doesn't have an effect if you don't combine it with biofeedback. Or in the other example, maybe it does have an effect in female mice and it doesn't have an effect in male mice. And if you kind of combine those two groups all together and you don't do the second factor, then you would miss that fact. There was a question. As I was talking. No? It went away? Okay. Yes?
So just confirming, when it comes to the main effects, right? If in our case, like the drug one was also with 2 levels instead of 3, does that mean like we wouldn't have needed to do any follow-up tests, right?
Yeah, so the question was if the drug factor also only had 2 levels, like the feedback factor, then how would that change all of these follow-up tests? So in that case, if there was a significant interaction, you would still need to follow that up to figure out what's different from what. If you did simple main effects, that would be the same as just doing pairwise tests. So you could just do 2D tests of all pairwise comparisons, and that would give you the same answers as if you one by one did these 2 points and then those 2 points. Yeah. So I think the answer to your question is yes. Yeah. If there's only 2 levels of the factors, then it's just a series of pairwise tests. All right. How are we doing? Good. Let me talk about one little complication. It's a complication that's actually helpful, and it kind of goes like this. Here's the full ANOVA that we started with. The main effect of biofeedback, the main effect of drug, and the biofeedback drug interaction effect. And the residuals, which is the so-called error term, right? The mean squared residuals, 65.1. That's the denominator of the F ratio. So this is 22.15. That comes out because you take 1442 and you divide it by 65. This 10, you get it by taking 700 and you divide it by 65. And this 4.6, you get it by taking 303.6 and you divide by 65. So that 65 is the denominator of all 3 omnibus F tests. This is the ANOVA for the simple main effect of drug when biofeedback is present. Right? That's when you take the 3 drug groups only for the biofeedback present part of the data, you isolate that away, and you do a one-way ANOVA. And we found that that was significant. What I want you to look at is the error term. The residual mean square for the full ANOVA is 65. the residual mean square for this simple main effect, one-way ANOVA. This one-way ANOVA where we isolate part of the data, and we ignore the other part of the data. It's actually bigger. The denominator of the F ratio in that one-way ANOVA is bigger than it is in the full two-way ANOVA. Now, I'm pointing this out because some researchers, some statisticians, when you do follow-up tests like a simple main effects test, or even pairwise tests, they prefer to use this error term from the full ANOVA rather than this error term in the one-way ANOVA. So they'll do this thing where they'll do this one-way ANOVA, they'll get this output, they'll ignore it, they'll go and take 960 and they'll divide it by 65, and they'll get a new F value, and then get a p-value from that. They'll use this error term from the full ANOVA instead of the error term for the one-way ANOVA. And the rationale for doing that is that this error term, remember what this error term is? It's a number that represents the variability in the data that's unaccounted for, the variability in the data that you can't explain by changes in feedback, by changes in the drug, or by the interaction of the two. It's the leftover stuff. The rationale is that error term, the so-called pooled error term, pooled across all these 6 groups, is a better estimate of the variance, the variability, the noise within each group. It's a better estimate than this one, because this 92 is only based on half the data. This is based on all the data, all 6 groups. This one's only based on 3 groups. So it's not as good of an estimate. So if we were to do that, if we were to get a new F statistic for our simple main effects by taking the mean squared drug and dividing it not by 92, but dividing it by 65, like down here, we would get an F of 14.75. That's bigger than 10. And then if we compute our p-value for that new F, we would get a much smaller p-value as well. What that means is it's a more statistically powerful test, because the denominator of the F statistic, the error term, the unaccounted for variability in that test is smaller. So it's a bit of a hacky thing to do. And we'll see in a minute, there's a way of doing it in R without having to do it manually like this. But that's a very common approach when following up an interaction. You use the one-way ANOVA to do the simple main effects just because it's a convenient mechanistic way of running that test, but you want the error term from the full ANOVA to be used, not the error term from the one-way ANOVA that's based on half the data. An argument, that's on one side of the argument. On the other side of the argument is that if there's a possibility that homogeneity of variance is violated, if there's a possibility that the variance within each group is different, is not the same, then in fact, using this pooled estimate of variance is something that you don't want to do, because it mushes together variance from all the different groups. And if they're different, by mushing them together, you're kind of ignoring that. And so if that might be true, then it's actually a better idea to use the error term from that one-way ANOVA. It's better to use that error term for just the data you're testing, because now that error term, the estimate of that unaccounted for variance, is a much more customized estimate. It's based on just the groups that you're testing now. And then the other one-way ANOVA on the other level is based on just those data points. And if the unaccounted for variance is different, for example, biofeedback absent versus biofeedback present, then you want to have these customized estimates of the error term. Yeah, so sorry for telling you all that. But this is another example of how there isn't one singular correct way of doing things in statistical analysis. And you might come across one of these two ways, or maybe you'll come across both of these ways. And maybe you'll come across someone who says, no, this other way that you were told, we don't do that, it's wrong. Or you might find someone saying the opposite, that the other way is wrong. So ultimately, you have to decide for yourself what to do. And whatever you decide to do, you have to be able to defend why you did it that way. And you defend it by considering the pros and cons and looking at your data in that context and deciding, okay, there's a test you can do for homogeneity of variance, right? We've seen that before. And if you do that test, and when you look at the data, there's nothing to worry about, the variance looks the same everywhere. Then, using this pooled estimate is probably the more appropriate thing to do. And that's great, because you get a more powerful test. If homogeneity variance looks like it might be violated, then probably you don't want to do that. You want to literally split the data apart and do tests separately. And yeah, you lose the extra statistical power you would get from doing it this way, but you protect yourself against type 1 error because you know that these error terms should be customized at each level of the other factor. There was a question. You had a question? Yeah.
Oh, I was just asking, I might be confusing something.
Yeah.
But I think maybe you're talking about, in one of the previous classes, about a type of ANOVA which is more resilient to if there isn't a homogeneity of variance.
Yeah.
Would we be able to use that here instead then?
A different kind of ANOVA that's more resilient to inhomogeneity of variance.
Or like there was a type of test where it's like, it doesn't matter as much. It's like less theoretical.
Talking about like unbalanced, like the Welch one or something?
Oh, the Welch test?
Something like that.
Yeah, that's right. There's a version of a one-way ANOVA called a Welch test that is used when homogeneity of variance might be a problem, and it adjusts the degrees of freedom to compensate for inhomogeneity of variance. Yes. That's probably what you would do. That if you were concerned about homogeneity of variance being violated, then when you ran this one-way ANOVA on the subs, well, let me put it this way. If the nature of the inhomogeneity of variance is that variance in biofeedback absent is different than variance in biofeedback present, if that's what the situation is, then, or if this was like males and females, then when you ran these two one-way ANOVAs, you wouldn't have to worry about it because as long as the variance is the same in each of these three groups, it doesn't matter that they're different from those because you're isolating them, right? And then when you ran a different one-way ANOVA just on those three, it wouldn't matter that they're different from the blue ones because you're not including the blue ones, as long as they were not different from each other there. If the nature of the inhomogeneity of variance was that variance is different, let's say high dose versus present versus absent, then in both cases, when you ran these one-way ANOVAs, you would have to do something about the inhomogeneity of variance. And in that case, we would probably run those one-way ANOVAs using the Welch version because it does this adjustment to take inhomogeneity of variance into account. That was a little complicated. Does that make sense? So it depends on the nature of the inhomogeneity of variance.
If it's like within what we're testing.
Yeah, because if there's inhomogeneity of variance within that one-way ANOVA, then you'd have to deal with that, like by using a Welch test. If it was just across the different ANOVAs, then that's okay because they're all separate from each other. Okay, so a quick recap of this concept and then we'll take a break. So when you're doing these simple main effects tests and you're isolating part of the data and doing a one-way ANOVA just on that part of the data, you get a more powerful test if you use the denominator of the F ratio not from the one-way ANOVA that's based on splitting the data, but if you use the pooled estimate of the error term from the full ANOVA, you get a more powerful statistical test because the denominator of the F is smaller. And so F will be bigger and the p-value will be smaller. You'll be more able to detect differences when they're there. The disadvantage of that is in the case where there's inhomogeneity of variance, that pooled estimate is no longer a valid estimate. In that case, you want a customized estimate for each of your different simple main effects tests. You do lose that extra boost in statistical power, but you have no choice. You have to take that hit, because the other hit you would take if you ignore it is that you would be using an inappropriate estimate of the error term, and that would affect your type 1 error. Oh my God, why did I put this slide up? I think this was just a summary. Oh, I know why. It's not as bad as it looks. This shows you in R how to do this customized thing, but without actually having to do it by hand. So here's our original ANOVA. You can get the marginal means across the interaction if you give it this formula not just with one factor, but with one factor and then times the other factor. Then you get all 6 means. So you get basically all 6 of these means here. You can then feed that object that you get from EM means into pairs, just like we've seen before. Tell it how to adjust. And there's a third argument we haven't seen yet, which is called simple. And that tells the pairs function to conduct those pairwise tests within each level of the other factor. So it kind of bypasses the simple main effects ANOVA and goes directly to pairwise tests within each level of the other factor. Type 1 error adjusted. So now we get pairwise tests of each drug group within biofeedback present, and pairwise tests of each drug group within biofeedback absent. So they are simple main effects tests, but there's a pairwise test version of that. They bypass the sort of ANOVA altogether and jump directly to the pairwise tests. Do you need to do the ANOVA first and then pairwise? Like I said, some statisticians will say yes, because that's how you protect yourself from type 1 error. Other statisticians will say, no, you can just go directly to the pairwise test, because as long as you correct them for type 1 error, then that's how you protect yourself. So if we compare these pairwise tests to the pairwise comparisons when we literally do a one-way ANOVA and we isolate, these pairwise tests use the error term from the whole ANOVA. That's the point. These ANOVAs, these one-way ANOVAs, have their own error term. 92, and 92, and then where's the other? I guess we're only doing one. So 65 is the error term from the full ANOVA, 92 is the error term when we do a one-way ANOVA of drug isolated for only the biofeedback present group. And when we then do pairwise tests, adjusted by home, now we can directly compare those 3 pairwise tests here with these 3 pairwise tests here. So those 3 pairwise tests are the same tests as these ones, except these ones here use this error term from the full ANOVA. These ones here use the error term from the split off ANOVA based on half of the data. Doesn't much matter in this case. What's significant here is still significant there. But what you can see is that the estimate, the difference between means, is the same in each case. 19.8, 19.8, 26.7, 26.7, 6.9, 6.9. The standard error and the degrees of freedom are different. The degrees of freedom here are only 12. Here they're 24. So 24 here, because that's the degrees of freedom of the residuals for the full ANOVA. There are only 12 here because that's the degrees of freedom for the residuals. For this ANOVA that's based on only half the data. And when you look at the p-values here, where we base this all on an ANOVA based on half the data, these p-values are bigger than the ones here. 0.0137, 0.0014, 0.0026, 0.0001, 0.278, 0.189. They're smaller here because our F ratio is bigger, and our F ratio here is bigger. Well, they're T, but our t ratios here are bigger because the denominator is smaller. Here the denominator comes from the overall ANOVA. Here the denominator comes from only half the data. So I'm sorry this is such a complicated looking slide, but basically on the left is doing the pairwise simple main effects tests using the denominator from the full ANOVA. On the right is doing pairwise tests where you literally consider only half the data and do a one-way ANOVA based on half the data. So it illustrates the difference between the results of the test, and it also shows you how you can do this in R without having to sort of construct these F ratios by hand. So I admit it's a little bit of a complication on two-way ANOVA, on a part of two-way ANOVA, right? On what you do in a two-way ANOVA in the case where there's a significant interaction, and you want to follow it up with simple main effects. Then there's kind of two ways to do it. Literally split the data apart and do a series of one-way ANOVAs, or do a series of either ANOVAs or pairwise tests and use the error term from the full ANOVA, from all the data. You use the error term from all the data, but you use the means from only part of the data. Which one you do really depends on how much you think inhomogeneity of variance might be a problem. Okay, I think we need a break. Let's take a 10-minute break. So 1:45. And then there's not much left actually.